Welcome to part 2 of our video tutorial on linear models in R. In part 2, we'll talk about multiple regression modeling. Multiple regression modeling is the logical extension of simple linear regression modeling, and as you can tell from the name, the difference between simple linear model and multiple regression model is that the latter one contains multiple predictors or multiple axes. So multiple regression modeling allows for inclusion of multiple independent variables that are used to predict a dependent variable of interest. But a lot of the ideas behind multiple regression modeling are the same. So we're still making predictions or inferences, but now we have more information to work with. Mathematically, we are trying to estimate the following model or the following line now. So we have y as our variable of interest, but now we have multiple predictors, x1, x2, and x3, and all the way to up to xn. We can have many predictors in our regression model. So now what we are trying to do, we are trying to estimate the coefficients before each of those axes. And then we still have an intercept term and also the so-called error term at the end. The math behind multiple regression model is a bit more complicated, and it requires some knowledge of matrix algebra. But of course, in R, as long as you use the LM function, you don't have to worry the math behind estimating coefficients in front of x's, the intercept, and so forth. When we talk about multiple regression modeling, we will cover we'll use something that looks like a realistic multiple regression modeling example. And in this example, we'll try to predict what determines price of rental housing in New York. So what we'll do first, we'll read a CSV file using the read table function from the web. And we'll indicate that separator is comma. We'll indicate that there's no header, which means we only want to get the data. And also we'll indicate that strings as factors false, which means that we want strings to be treated as strings, meaning as text, and not as factors, meaning not as levels of one particular variable. So after we read this file, after we import this file into a data frame, we display the content of this file using the head function. So that's what we will see. So this is the table that we have. Again, this table, this data set contains data about housing available for rent in New York City and surrounding areas. I guess all of those boroughs are part of the New York City. So when it comes to the borough, we'll have Manhattan, we have Bronx, we have Queens. Here we have neighborhood, which is another classification within those boroughs or cities comprising New York City. Then we have zoning, then we have total units, which means how many condos or units for rent each house contains. Then we have the year when that house was built, gross square footage for each building, estimated gross income for each building, gross income per square foot, estimated expense, meaning total expense for the building. Then we have expense per square foot, net operating income, full market value of the building, market value per square foot, and once again, we have the borough where that particular condo building is located. So we'll change the names of those variables a little bit to make them shorter and easy to read. So we'll use names function. We'll apply names function to the housing data frame. And this vector will contain the names for the columns that we will use. And now we'll use head command again to see how the names have changed. So now it looks a bit simpler and more readable to a human. So let's say we're interested in predicting value per square feet. And by value per square feet right here, we're talking about market value. Market value per square feet of each of the condo unit comprising those buildings. So let's start exploring the per square foot variable, because that's the y variable, that's the dependent variable that we're trying to predict. So let's build a histogram, And when we build a histogram, we see that the distribution of this variable is not normal. By the way, normal distribution of y, meaning the dependent variable, is one of the assumptions of regression. So if it's not normally distributed, it means that strictly speaking, we cannot use regression analysis and we need to do something about it. So here the distribution is not normal, is the so-called bimodal distribution. In fact, we see that there are several peaks or distributions within it. So which means that we need to do something to subdivide this variable into meaningful groups so that each group becomes normally distributed. Okay. How we do it? Well, it's something closer to art rather than science. We need to continue exploring data to see what exactly we see in this distribution. So what we can do first, we will use ggplot2 package to add color to each of the boroughs. So what we will do, we will build a histogram, and each borough, meaning neighborhood in New York, will have a different color. So when we run that, we'll see that those modes or those peaks represent different boroughs in New York City. So one pronounced borough that we see is Brooklyn. So Brooklyn has its own distribution right here. Then Manhattan has its own distribution. Then Queens seems to have its own distribution, and so forth. So when we do faceted plot, we see that once we split data by boroughs, we see that we don't have much data for Staten Island. We don't have much data for Bronx, and then when we look at Brooklyn and Manhattan separately, those distribution looks more or less normal. Here we have a peak distribution. Manhattan has more or less normal distribution. Queens is clearly deviating from the normal distribution, has bimodal as well. So anyways, this is something that allows you to take a better look at your dependent variable. So perhaps you will limit your analysis to Manhattan only because this is where the assumptions of regression model seem to hold true. But for now, we'll just ignore those assumptions and we'll proceed exploring the data. So let's continue exploring our data. We'll take a closer look mostly at the independent variables, the variables that we're trying to use to predict the value per square foot. So let's take a look at the square foot variable. This variable contains the value of the total square feet that the building has available. So when we plot a histogram of this variable, we see that it's not normally distributed. In fact, it looks like an exponential distribution. So this means that most units, most houses, condo houses, are on the lower end. However, you have extreme outliers. And the same thing for the units variable that contains the number of condos that each building contains. So it's also not normally distributed. You have some outliers, meaning some buildings that have more than 1,000 units. So let's try, again, we're not trying to achieve anything specific. We're just experimenting, looking at our data, doing exploratory data analysis. So let's plot the square foot variable in a histogram by eliminating all buildings that have more than 1,000 units. So we want to include only buildings that with less than 1,000 units. So now the distribution looks a bit better, but it's still not normal. And we do the same for the units variable. We eliminate all the houses, all the buildings that have more than 1,000 condos. So we only include units with less than 1,000. Again, it looks a bit better, a bit closer to normal, but it's still not normal. In fact, it looks like log normal distribution. So let's start building scatterplots. We're just trying to see how different variables are related. So we're gonna create a scatterplot for two variables, square foot and value per square foot. So we'll use a scatterplot. So immediately we see that the relationship between value per square foot and square feet, which means the total square footage for the building versus the price or market value per square foot. Immediately from the scatterplot, you see that this is not a linear relationship between these two variables. It looks like some kind of exponential relationship, something that will require a log transformation down the road. So the same thing we can do for variable units and value per square foot. Again, it doesn't look like a sausage or stretched sausage, which is more like a cloud. It looks like something that is exponential. We do see some outliers way there. We also see outliers for the value per square foot, right? Versus square feet, so some extreme values right here. And then, you know, one thing that we see is that for those extreme outliers, meaning for very large building with a lot of square footage, the value per square foot tends to be much lower, right? You can see it from that scatter plot. So again, let's eliminate from those scatter plots very large buildings. Let's see how it looks like. Still doesn't look like a linear relationship, and the same thing here. So we saw two things. We saw that you know, some variables are related in a non-linear fashion. We also see there are some outliers. So how can we deal with outliers? Well, what we can do, we can count them. How many observations in the data set have more than 1,000 units, which means that we're trying to count, we're trying to sum the units that have more than 1,000 condos, houses or buildings that have more than 1,000 units in them. So we run this and we get 6, which means we only have 6 outliers. So we're gonna go ahead and remove those outliers using the following command. Now you need to be careful about removing outliers. By removing outliers, you make your data look a bit better, for example, a bit more normally distributed. However, some scientists, some statisticians argue that no outliers should be removed, because by removing outliers, you're basically deviating from real life. In fact, some statisticians go as far as saying that this is like a way to manipulate data. By removing outliers, you know, you can manipulate the outcome of your regression model to get the conclusion that you want simply by saying, oh, it's an outlier. So I guess what I'm trying to say, you know, what some researchers can do, they get a data set from a real life scenario. They run their regression. They don't get the results that they want. For example, they don't get any significant predictors. So they say, oh, let's remove outliers. Let's see what happens. So by removing outliers, most likely the fit of the model will improve, because those outliers, they they kind of drag the line and they make the line less a bit less of a good, like a worse estimator of the relationship between variables. But again, by removing outliers, you are deviating from what you observed in real life. So in other words, there's an opinion that outliers should not be removed. I think it's okay if you remove outliers, as long as you're making it clear that outliers have been cleaned. You know, if you're hiding that fact, then people may suspect that you're doing some sort of manipulation by trying to get by removing outliers. You're trying to get the results that you want. So let's remove those extreme outliers, extremely large buildings that have more than 1,000 units in them. And then let's just look at the pairs of variables. And this is where log transformation can be explained and visualized. So log transformation of a variable means you take a log of each value of the variable, and that's something that can transform a non-linear relationship into a linear one. So for example, if you're trying to predict, I don't know, value per square foot based on square feet variable, you see that the relationship is not linear, because this cloud, this scatter plot, does not look like a cloud, does not look like a sausage. However, if you log transform square foot, because we already saw that this variable, remember when we did this, we saw that this variable is log normally distributed. Sorry, it's right here. So some transformation need to be done to make it normal. So when we do this transformation, we see that now the scatter plot looks like a sausage, very stretched out sausage, more like a cloud. But this is something that can be approximated using a line. The previous relationship cannot be approximated using a line. But by the way, it's a trick, it's a mathematical trick. When you log transform a variable to make the relationship linear and then you build a line, you're actually building a non-linear model. But that's, those are some nuances of regression modeling, some tricks, how to turn a non-linear relationship into linear so that the linear regression model can be used. You see a similar pattern for these two variables. So when you plot square feet against log transform value per square foot, it's still it still doesn't look normal. And when you do both, when you log transform both, then again it looks like a cloud. So transforming, log transforming both variables will give you a linear relationship, right, like this. Now, if you log transform only one variable, something that you're doing here, again, the relationship looks more linear, but the interpretation of coefficients becomes hard. So it's better to transform both sides. In that case, there is a clear interpretation of what your model outcome means. So it's like an exponential function. You can convert your estimates back into an exponential function. But again, I'm going to leave it for now. In fact, in my dissertation, I did something like that to bring two variables into a linear format, and then to get the exponential equation that basically showed whether economies of scale are present in the production of IT products or services at the department level. So I'm going to leave all those details for now because it requires a lot of explanation and math. But this example demonstrates what log transformation does. It converts a nonlinear relationship into a linear one. So if you see, if you see some variables are log normally or exponentially distributed, something like that. So that's the first sign that log transformation may be necessary to bring those variables to normal distribution and to use a linear regression model with them. And then, when you do those pairs, you kind of see the same pattern. I'm not going to go through all those pairs, but you see that log transformation may be required. So let's start modeling. So we explored something. We saw that, our data set has some weaknesses with respect to, in relation to linear regression modeling, because some variables are not related into a linear fashion. But nevertheless, we'll go ahead and proceed. We'll use a linear model to estimate the relationship between value per square feet, which is our dependent variable, and other independent variables. So we do it like that. And we see that all variables are significant predictors of value per square feet. So you see you have 3 stars for each of the coefficients. So here you have the coefficient itself. The coefficient is expressed in the same units as the dependent variable. So for every change, in square feet, you have this kind of change in the dependent variable, which is dollars. It's hard to interpret right now because it uses that scientific notation. But nevertheless, that's the output. If you want to make this output nicer, if you want to make it more readable, then use the Stargazer package to generate a nice output. I showed you before how to do it, so I'm not going to do it here. Also, there's a package for visualizing coefficients called Scatterplots. So we'll install and load this package really quick. So we'll do the installation. So here, for each variable, the thick line represents 2 standard deviations. So if the thick line is touching 0, it means that we cannot rule out that this coefficient is 0. So it means it's insignificant. So the Borough Staten Island, which is a dummy variable, it has 0, 1. It's not significant, and that's what we saw in our output here. Borough Staten Island is not significant. Everything else seems to be significant. Now here, I'm not sure what happened. I think the data is very clustered, or it's been log transform pulled in. So I'm not sure why you don't see this interval. So maybe this variable is highly clustered. But here you see that all other variables except Staten Island, they don't include, the 2 standard deviation confidence interval is not touching 0, which means they're statistically significant. But I don't use personally this package to analyze coefficients. I just use this normal output, normal table to look at it. And again, with Stargazer, you can convert it into a human readable table that you can also insert into a Word document. So that completes part 2 of our video tutorial on linear models in R.